Now let's look at more detail at aperture illumination. And we're going to look first at the antenna radiation pattern from a line source here, which goes, and the length of the source is from minus a over 2 to plus a over 2 along the z-axis. And the direction of illumination is in the, and the current, a distance z from the E sub phi is in the far field, so that we can just take this current, apply the Fourier transform to it, and that gives us the E field. Isn't that nice about the aperture illumination? If you know the aperture illumination, you can just take the Fourier transform of it, and boom, you've got the E field in the far field. And that far field approximation is A, the size of the distribution of the current, is much, much greater than lambda, and the distance that you're tracking antennas, 10, 20 miles or whatever, 100 miles, is much, much greater than a squared over lambda, which is true in just about most cases. And here's the equation you get with A of z equals 1. And you can, if you can see that this is a cinchy kind of thing. And if I put a cosine aperture distribution, cosine pi times A over z, you get something more complicated. But when you take the Fourier transform of it. But the neat thing is, what do they look like? When we take the uniform illumination, we get much higher side lobes. When we put the cosine illumination on, we don't lose very much at all in the main beam, but we broaden it, and we get very much lower side lobes. Isn't that neat? The weighting of the aperture illumination increases the beam width, lowers the side lobes, and lowers the antenna gain. And the antenna gain at the center is only 0.9 dB, lowering things. So putting on, people just pretty much don't use uniform illuminations, cosine. There's a number of them they use. Now you can apply the same formalism in 2 dimensions. And for anyone that's got this far in the course, if you got through the E&M, it's trivial what I'm doing here. I'm just saying that the aperture pattern you can express as a product of, because things add vectorially, of the two-dimensional problem. The problem reduces to 2 one-dimensional problems because the aperture is separable, and it's the calculation of the signal is non-trivial usually. And here's the E field, here's the integral you need to do, and we're looking over a plane, but it's a doable integral, and bingo, here's what we get with a circular aperture. And I'm all going through these because I'm going to show you a table later. We had a circular, like a circular antenna, not a square antenna. You'd have a circular aperture, and if we put a uniform illumination on it, you get one thing. And we can put here we get this for the circular illumination, where this J sub 1 is a first order Bessel function. These are easily calculable things. Tapering the aperture will broaden the beam width and lower the side lobes again. And here we see sort of the all-in-one view graph for all kinds of illuminations. You can have parabolic illuminations, cosine illuminations, triangular, circular, and cosine squared on a pedestal. And this shows you the gain relative to uniform in dB. And this shows you the half-power beam width, and notice the uniform is 51, and this shows you how much over the 51 lambda over d you are for your beam width. And the first side lobe down, you notice like our Hamming weighting, cosine squared on a pedestal is 42.8 dB down, and a cosine, okay. So that taper efficiency, the spillover blockage, and the total loss versus feed pattern edge taper. And this is for one design of one antenna. Show you what you want to do. In the one case, you've got a loss due to the spillover effect. In another case, you've got the loss due to the feed blockage. Another case, you've got the loss and your taper efficiency. And when you add them all up, you've got this line, which is your total loss. But remember, this is 0 up here, so you can get to a loss of about 1.4 dB for the antenna. And this is taken, Cooley wrote a paper on this, and Skolnick in reference 4 has this photograph with re-rendered to give you the idea that you have to trade these things off. Now, not only do we have these trade-offs, but we've got different reflector feeds and reflector geometries, if we haven't had enough with the reflector itself. The feed horns come in all different sizes and shapes. We have flared pyramidal horns, flared conical horns, corrugated horns, segmented aperture horns, finned horns, compound flared multi-mode horns. Now, I'm not going to give you a rundown of what and why you use each and every one of those in. But if you go to Skolnick and reference 4, I bet that's the handbook, you'll see a paragraph or two on each one of them. Simple flared pyramidal horns, TE101 and 11 horns are used in pencil beam and single mode applications. Corrugated, compound, and finned horns are used in more complicated applications, where you want to have polarization diversity, ultra-low side lobes, and high beam efficiency. And segmented horns are used for monopulse applications, where these are effectively 6 different horns that come out. This drawing of mine doesn't quite do it. Okay, now this is an important part because this is a neat geometry that helps you in lowering significantly the blockage from getting energy to the focus. And you've probably, if you know about telescopes, you know about Cassegrain feeds. What you do is you start off with a basic parabola, and there's a virtual point of that parabola, and you put a hyperbola at the real focal point back here. And what that does is that transmits energy out, this hyperbolic subreflector, so that energy will go back to the parabola as though it came from the virtual focal point of the parabola and go out parallel. The virtue of this is you can build these relatively close together. You only have to have the hyperbolic subreflector can be smaller and save you a lot of feed blockage and losses in curves of your feed and length of your feed too. The good things about Cassegrain feeds are you've got as I just said, lower waveguide loss because the feed is not at the focus of the paraboloid, but it's near the dish. The antenna noise is lower than conventional feeds because the length of waveguide from the antenna feed to the receiver is shorter, and the antenna spillover from the feed, seeing the colder sky rather than the warmer earth, that helps you. You remember that from the radar range equation section. And it's a good choice for a monopulse tracker because you're going to have complex monopulse plumbing. That means waveguide structure. And that may be placed behind the reflector and avoid a very complex feed system running up to the focal point of the parabola. Now I want to take here and show you a couple of different Cassegrain feeds that boggle the mind. This is again the antenna. This weighs something over 900,000 pounds, almost 1 million pounds this antenna does. And it's got it's really a dual antenna, a VHF parabolic feed and a UHF Cassegrain feed, and it's got what's called a frequency selective surface is used for the reflector at UHF. Okay? Now notice, if you notice, this is a blow up of that little area up there, which isn't little. And here's a man on a crane, brave fellow. And this is the dichroic front surface reflector that's reflective at UHF and transparent at VHF. The teacup to the right is the cover on a 5-horn VHF feed located at the antenna's focal point. So at VHF, you've got a plain parabolic reflector feed at the focal point, but at UHF, this is your hyperbola, which it's reflective at UHF, and the energy goes back to the UHF feed. Isn't that neato? And so the front surface subreflector, frequency selective surface subreflector, is composed of 2 layers of cross dipoles. For the interested student, you can look that up in Skolnick's handbook. I'm not going to get into the, or better yet, you can go to. I don't think Balanis's antenna book will have it, but certainly John Velakis's antenna handbook, which is 1,000 pages thick, will have, those kinds of neat subreflectors, the frequency reflectors, frequency selective surface subreflectors. Air surveillance coverage of a simple fan beam radars usually won't handle high altitude short range coverage like air traffic control radars. And a simple fan beam doesn't give you much energy at near-in ranges at high altitudes. So what you do is you use a fan beam where you shape the reflector and make it proportional to the square of the cosecant of the elevation angle. And that gives you a constant gain for a given altitude. And that's called a cosecant squared beam. And so for this portion of the beam, you have the parabola. The gain is G1 times cosecant squared theta divided by cosecant squared theta 1. It'll have the same gain. And for theta between theta 1 and theta 2, the gain is equal to that. Okay? And this is a picture of one. And this isn't a parabola. What actually we've done with this is you move that lower, what you do is this part of the parabola you keep parabolically shaped, and this part you move in closer, and consequently more energy goes up at the higher elevation angles so that you get that effect of a constant gain in close to the radar. And that's what's called the cosecant squared antenna pattern. And FAA, airport surveillance radar users, and air traffic control radar users use this all the time. And here's a picture of a fellow standing next to an airport surveillance, number 9. Believe it, this is Frank Sanders, neat guy. He gave me that picture to use. But that actual picture happens to be, he works for the Department of Commerce, and he gave me that to use. And here's a pattern of how, what you can, instead of changing the shape of the feed, you can put a set of different horns down at different numbers of different amounts down along a line. And what you'll do is you'll get different beams at 0 degrees, 5 degrees, 10 degrees, 15 degrees, and 20 degrees. That one's 0, 5, 10, 15, 20 degrees when you put different feed horns. And that's known as a set of stacked beams. And that can be used to measure the height of a target, that kind of an antenna. Okay. And this is one of those types of antennas. I referred to it earlier when I was talking about the different shapes. And this particular antenna, you see, has a very large number of feeds, and it generates actually 7 beams where it takes 2 or 3 here, 2 or 3 there, the energy for 2 or 3 here, 2 or 3 there, 2 or 3 there, 2 or 3 there, and combines them. And it's a very cost-effective way of measuring height while simultaneously performing surveillance option. And this antenna was developed in the 70s and underwent upgrades in the 90s, where the antenna was replaced with a slotted waveguide antenna, which could do exactly the same function, but had very low side lobes. And here's that antenna on a TPS 78. This is courtesy of Northrop Grumman. So this is a planar array, and it's a array antenna, which gives you, again, it mechanically rotates, but gives you a number of beams and elevation. And it's got very nice, very low side lobes. Okay, next I'm going to go to scanning reflector antennas. Scanning a radar beam over a limited angle with a fixed reflector and a movable feed is what I'm talking about. A paraboloid can't be scanned too far without deterioration. And the gain of the antenna with an F over D of 1/4 is reduced to 80% of when the... So to scan wide angles in one dimension, you can do that with a parabolic torus configuration. It's like the outer shape of a donut, the outer, the outer surface of a donut, the inner part taken out, just that outer surface. And the scan angle is limited to about 120 degrees, and it's an economical way to rapidly scan very large antennas over wide angles. And it uses as its scanner mechanically the big main one that was used. I'm going to show you. It was built back in the 50s, late 50s, 60s, has an organ pipe scanner, it's called. And it's a mechanically scanning feed between many fixed feeds. And here's a picture of the feed. And the feed horn is rotated around to these different feeds which go up and input to the antenna at different locations along the focus of the focal length of the torus. And this is that parabolic torus antenna. Isn't that interesting? This is before we had phased arrays, which I'll see can do give you 3-dimensional scanning over wide angles. And the output of the feed horns along this are located along this arc. So what you do is you put this down here and have waveguides come up and go to feed horns that would go out, and they'd progress onward. Here's the picture of one, what I'll call the prototype. Ignore this large parabol antenna here. And here is the feeds, rows of feeds for this giant torus reflector. And this was actually built as a ballistic missile early warning radar up in the Arctic when the United States was concerned about Russians launching missiles over the pole. That's the shortest great circle path. And so radars like this is a set of 3 of them. Here in this house is where the feed horn structure is, that organ pipe scanner system. And here are the actual antennas. And one was located at Clear, Alaska, another one in Thule, Greenland. Okay, now let's summarize part 1. We covered an awful lot of territory. We've discussed antenna parameters, gain, side lobes, beam width, how the beam width varies with the antenna aperture and size and wavelength, and talked about polarization and the different forms of it. We've talked about mechanical scanning antennas as a nice, very inexpensive way of getting beam agility. There's slow to moderate angular velocities and accelerations, though. If you want to, remember, think of those antennas. Those antennas, there's a lot of motive inertia in those antennas. Like that one, it's 120 feet across. You want to go over 90 degrees. It goes over on a railroad. So it's not going to go 20 degrees a second, very slowly. So that's a negative part of them. But they can, over moderate angular ranges, get you very good coverage. And different types of mechanical scanning antennas we've gone over. Parabolic reflectors, Cassegrain, and with offset feeds too. We've talked about stacked beam antennas. We've also talked about aperture illumination and blockage and beam spillover, as those are antenna issues. And this ends part 1. And here are some homework problems on this lecture 1 on antennas. And they're from some different sections in Maryland. And next, we're going to do phased array antennas, frequency scanning antennas, hybrid methods, and even other topics in the second half of the antenna section of the course. I'd like to thank very much Dr. Pamela Evans and Dr. Alan Friend, good friends and colleagues at Lincoln Laboratory, where I worked before I am now retired. I'm retired now. And a lot of the view graphs have come from their ideas, and they're just, they are real. I wish I had their knowledge of the antennas. Thank you very much. Now I'll take more than a break. I've got to edit this section and get it up on the web, and then we'll move on to antennas 2. And just a preview of upcoming attractions. We'll do radar clutter after that. I think the next section's got about the same. It's got about 50, 60 view graphs in it. And I've got about 100 in clutter. So there are going to be some long lectures. But by then we'll be through 10 of the core lectures, more than halfway through. Thank you very much.